All right, let's do a problem with friction piles. So we're going to have our structure with a weight of 1.5 million pounds, width of 36 feet, and these piles are considered to be friction piles. Why? As we noted, we look at the tips. Look at the tips of the piles, and what soil is the tip in? It's in clay. If it's in clay or silt, then these piles are considered to be friction piles. So to determine whether piles are friction or end-bearing, you look at the tips and you look at the soil type. Again, if the tips are in clay or silt, then we have friction piles. If the tips are in sand or gravel, then we have end-bearing piles. All right, so I just want to find the center settlement here, and these are our soil properties. We have this sand layer over the clay. We have a water table at the ground surface, and we're going to need to find the point of interest depth, and we're going to need to find H, and we're going to see the effect of having friction piles rather than end-bearing piles. And this is how we handle it. Now, this is a rule of thumb. So this is what people use. In other words, if I have a friction pile, I don't transfer the load all the way down to the tips because I don't have a stiff soil at the tips. But I do know that I transfer the load, from the ground surface into the ground because I have piles. And so what people do is they say, well, I don't go all the way to the tip, but I'll use two-thirds of the length of the piles is what I'll say it goes down to. That's what people use. So the way that we analyze this problem is we don't put the load down here and draw our pressure bulb from here. Instead, what we do is we're essentially analyzing a mat at this depth and the pressure bulb going from that mat. It's not a real mat, obviously, but that's the way that we envision it, and that's the way that we analyze it. So, in other words, this total pile length is 60 feet. 2/3 of 60 is 40. So I put this fake mat at 40 feet. And then I draw my pressure bulb from that fake mat. So what do we find? The pressure bulb goes to a depth of 2B, which is 72 feet. B is 36. And since that's it, this is 40, that's 72, that takes me to 112. So the bottom of the pressure bulb is 112 feet, and the top of the pressure bulb, or the top in this case, where we're considering it, the top of the pressure bulb is 40 feet, so we have 112 plus 40 divided by 2 to get the point of interest depth. So 76 feet. So 76 feet, there is my point of interest right there. And notice it's a distance of 36 feet below our, fake mat. So that is our point of interest depth, 112 plus 40 over 2. And then our H is 112 minus 40, which is 72. So my H is, in this case, it's 2B, which is 72 feet. Okay, so that gets us started. That gives us our point of interest depth. So before the structure is built, we want to determine our sigma prime I and our sigma prime P. So envision that there's no structure there. If there's no structure there, then my Sigma V is 10 times 110 plus 66 times 100, so we're just using our gamma saturated because our water table's at the ground surface. And that gives us our sigma V. Our U is 76 times 62.4. And I subtract one from the other. I get that for my sigma V prime, which is our sigma prime I when we do our settlement analysis. The OCR is 1.3. I multiply 1.3 times our sigma prime I. We get 3844. Okay, so this is the table we just filled in. And so we have our sigma prime I at our point of interest, our sigma prime P at our point of interest. And now I want to evaluate the settlement at the center, edge, and corner. So our P is what? The weight of the structure. Our area is B squared, 36 squared. And our Q is that. Now the Z to our point of interest is the distance. Remember, the Z is what I have my mat here. The Z is this distance to there, which is 36 feet. So I have 36, 36 between for the center and the edge. And then we do our little trick, which is to use our pressure bulb, we divide that by 2 to get our corner stress. The B is the 36, which we already said, and so Z over B, I just divide that, I get 1. That one I get 0.5. Then what do? We go into our pressure bulb, and remember we do our trick. Oops. And, well, I guess I don't have it written out, but we've done it enough times now that you should be able, we're going to use it like this. What do? We have our Z over B is 1. Our below the center, Z over B is 1 at the edge, and then we do 0.5 for the corner, but then again we divide our contour value by 4. So when we do the corner one, we divide the contour value by 4. So I'm going to get, 0.34 for this one, and then, 0.25 for this one, and then that's 0.7 divided by 4. So we've done this, and you know how to do it. So let's go back to our problem. So, 0.34, 0.25, 0.7 divided by 4. Those are our pressure bulb factors. So that our delta sigma V then becomes what? It's the pressure bulb factor times the Q. And so that gives us the delta sigma V. And then I'm just going to take these values and write them in this column. And then I take my sigma prime I, which is around 3,000 roughly, and I add that to give me that. The 3,000 plus that gives me that. 3,000 plus that gives me that, approximately. So I add my sigma, so in other words, sigma prime I plus delta sigma V is given there. So that gives me, so we now have sigma prime I, sigma prime P, and sigma prime F. It's enough to do our settlement calculation. So we draw our plot, center, edge, corner. And if you remember, the first thing we put on is our sigma prime P. Sigma prime P goes at the corner there. And then we just determine the locations of the sigma prime I to begin with. We know the sigma prime I is less than the sigma prime P, so it's going to go to the left in each case. It's going to go like that. Then we look at our sigma prime f. Well, if we look at our sigma prime f, all those sigma prime f's are less than the sigma prime p, which means that our sigma prime f is going to be up in here to the left of the sigma prime p, and that means we're only using the C epsilon r region of our curve here, and so we have the C epsilon r log sigma prime f over sigma prime I. That gives us our epsilon v's, and then our delta h is our h times epsilon v. So we get our delta h's, that's in feet, and then we do the calculation that we've already gone through, which is our, if we take A as the center, B as the edge, C as the corner, we get rho AB over L, rho AC over L, rho BC over L. I'm not going to go through this in detail, but we can plug all in those values. It's 18 feet. Using the Pythagorean theorem, we get 25.45 feet divided by 18 feet. And for some reason, a couple numbers are missing, but you can fill in these little values there. But no matter, we end up with 1 over 610, 1 over 464, 1 over 708, and what do we see? Each one of these is less than 1 over 300, which means that this foundation is okay. So this works. We get a good foundation, and that's one we can build. Now, what we can do is, what you can do is you say, okay, well, if you really want to be tight, this is less than 1 over 300. You could push it a little bit and make the piles a little bit shorter or something like that, and see if you can still get less than 1 over 300. That's another possibility. But no matter what, this is okay. You can go with that. You can go with this. It may be a little bit more expensive than you want. So you should check out something that's a little bit less conservative in the sense that maybe shorter piles, smaller basement, something like that. Or not smaller, we didn't have a basement there. Okay, never mind, shorter piles. All right, that leads me into the next problem, which is the same as the previous problem, but we're going to put in a basement. We're going to put in a basement that's 9 feet deep. So let's see what the impact is. How do we analyze this now with the basement? Again, now the way I want you to do this problem, now like I say, when you're in practice, you got to do something a little bit more precise in the sense that you take a lot of different points of interest. But using just one point of interest is actually informative to it. We're just going to use one because it's informative to us because it gives us an intuitive feel for what is the impact of the basement on this design, and it gives us a feel for what soil is primarily getting stressed. So I sort of like the one point of interest for teaching because I want you to get a gut feeling for this stuff. And if you've done these problems enough, and which I'm making you do a lot of problems, you're going to get an understanding. Oh, I got it. This is the soil that gets stressed, and if I put it in the basement, this has this effect. So that's why I do this. But you have to think about your problem as you're working it so that you have an understanding of what's going on here. Okay, so same problem, friction piles, find the center, edge, and corner settlement. Same soil properties. And in this particular case, we've again put the piles down to 60 feet, but we have this 9-foot basement, so the piles are now shorter. The piles are now 60 minus 9, which is 51 feet, which means my length of my pile is 51 feet, 2/3 of L is 34 feet. And so I go down 34 feet, so I'm at 43 feet now for where my, fake mat is. And then I'm going to draw this pressure bulb from that. So when I do that, now I have, excuse me, I have my point of interest depth is going to be the, so we go down 2B. So in other words, we go, this depth here is 72 below 43, which is 115 feet. For some reason, it's not on there. So let me put that on there. So that depth is 115 feet. And that means that my point of interest depth is going to be the depth is going to be the 115 plus the 43 over 2, which is 79 feet, and then my H is going to be 115 minus 43, which is the 72 feet. So we get something slightly different than what we had last time. So there's my point of interest depth. All right, so what do I do? Well, now I have to change a little bit. Now my depth is 79. I'm not going to go through it. You got your sigma v, you got your u. You can pause the video and look at this. Sigma v prime, which are sigma I, OCR, sigma prime p. So multiply those all out. You can figure those out for a different depth now. It's at 79 feet. That same. Okay, so yeah, that gets us going with the beginning of the problem and how we handle the weight of the structure. Remember, the weight of the structure is 1,500 pounds. But how do we handle the basement? What's the effect of the basement? Well, removing the basement gives us another pressure bulb. It sort of gives us a negative pressure bulb. But so in other words, here's my pressure bulb for the basement. So now what we're going to do is we're going to keep the point of interest the same. And in other words, this is what I want you to do, is that what we want to know is we've established the point of interest, and we want to know what is the effect of having the basement on that point of interest, that same point of interest. In other words, this is the way I want you to do the problem. We've created our point of interest there because that's where most of the changes in stress are happening. But we can, and it's very informative here because there's my point of interest, and that's sort of, the center of the settlement region. And what we find is, you can sort of see it now, is that the effect of the basement, this basement here, where I draw my pressure bulb from the basement, on my point of interest is less than the effect of the weight of the structure. In other words, because my point of interest is way deep, right? It's way deep at the bottom of the pressure bulb in a sense. I mean, it depends on, each problem's a little bit different, but what has happened is that we have transferred our load using our piles. The effect of that is to transfer the load deep into the ground. Well, the basement is up near the top. So if I have, so we could run into the case where if we have really long piles and we transfer the point of interest deep into the ground, that the basement may have no effect. So there may be almost no advantage to having a basement if we have long piles. So that's what we learn. Whereas if we have a mat, there's a huge, huge advantage to having a basement. But if we have piles, the basement may help us, it may not. And that's what we are looking at here. So we draw our pressure bulb now, we keep our point of interest down here, and now what do we have? Our Z is 70, our point of interest depth is still 79, and the H is the same and all that, but what our goal is to figure out, we need to use this pressure bulb now, this Z, and figure out the influence of the basement. This is all the same as last time. So now let's put this together. And yeah, so this is the, oops. Okay, there's a little mistake here, so I'm going to pause the video.